Morning, Kelvin.
Good morning. Sorry I haven't been to class a day or two.
Yeah, if you can, better to just email me that might happen. But if it's because we're sleeping, then it's probably hard. But you
Uh,
can tell me.
yeah, no, I actually caught COVID, so everything's been screwed up. But
Okay.
I am all clear now, so I should be able to still be able to make it in person for the exam.
Okay. Are yeah. So are you good with everything else? I'm not sure what yeah, I guess if we need to have a longer conversation, let me know if you were I actually have not checked it if you missed some of the other stuff or whatever, but obviously we can work something out if you had COVID. So
No, I got everything turned in. I was able to glean what I needed to.
okay.
Um, we are covering Maxwell's equation, right? That was homework 8, pretty much.
Yes, yeah.
Okay.
So I don't know why like this my video keeps is it frozen on your side
It
also?
is it is a little frozen, yeah.
Yeah, it's kind of weird. Anyways, yeah, we will on this exam we will cover Faraday's law, which is equation or homework 7 and 8. Yeah, and with the time varying fields. And then magnetostatics also. So
Okay. So yeah, I'm not super worried about it. It's a lot like similar. It's very similar to the last exam. So
yes, yeah. So yeah, that's the thing too, is like on this exam, I'm not going to be asking questions like specifically about electric fields, but that also doesn't mean you can just like forget everything you learned, because like the magnetostatics and the electrostatics are really similar. Like the main difference is practically just in like what direction the resultant field is in. Like with electrostatics, you have to do the dot product. The magnetostatics, you'll end up doing cross products. So there's just you just can't like ignore it or pretend like it didn't happen, which I don't think you're going to. But I'm not like planning to ask specific questions on like Coulomb's law again. But Biot-Savart is like almost identical. So yeah.
so the final exam is comprehensive for this class, right?
Yes, the final exam is comprehensive. However, I mean, I'm sure like other comprehensive exams you've had are like this, which is that the we're going to be covering a section on transmission lines before we get there, and so that's the stuff that I'm going to be the most interested in, giving the exam about. So likely I haven't written it up, but likely 50% of the questions are going to be on transmission line theory, and then there will be one or two questions each related to exams 1 and 2. So but yeah, something like that. But you're feeling okay, feeling better?
Yeah, it just took me out for a couple days, and then I'm
Yeah,
feeling good now.
yeah, that's good. Did yeah, had you been like had you got the vaccination? Did it go like
No, so I didn't get the vaccination, um, and I just caught it. Uh, I caught it on like Thursday of last week, so I just had to wait like 10 days.
right? Yeah, that makes sense.
So
Yeah, it's kind of interesting, like how it affects different people.
Yeah, I only felt bad for like 2 days, and then I couldn't taste or smell, but that was about all that it did to me.
Yeah. Can you still not taste?
No, I still can't taste. It's coming back a little bit, but
Hmm.
not fully yet.
Yeah, interesting. Yeah, I like don't think I don't really know whether I got it or not, but like right when it first happened, like when all this started, when there was like probably, more cases than they wanted to let on or knew because they couldn't actually test them. I'd like spent a weekend in Jackson Hole, like skiing, and like, we were all like, I was in this hotel and I remember there's like, all these like French people and Chinese people and like people from all over the world. And then I like ate lunch in the cafeteria and I was, like super close to all these people. And there's like Australians across from me and like Chinese people across from me in the other direction. Is like just jam packed. And I got like super sick a few days after that. So, but I couldn't, I have no idea whether that was it or not. So
Right, yeah.
I apologize to everyone else. I don't know why my video keeps freezing. So, try to turn it off, turn it back on. I don't know. We'll see. So did any of you work on the practice problems or the practice exam?
I walked through a couple of them.
Yeah. Are those helpful?
I think so. I think they help me to know kind of a little more what the exam is going to be oriented towards. I enjoy it.
Well, we still have a few more minutes. People might be working on the quiz, but if you have any questions related to the exam, I'm happy to start, talking about it. Or I know I've already answered a few of Calvin's questions. I think I talked to AK in email. Sorry, AK, do you prefer being called AK or Abdullah?
Uh, Whatever is easier for you.
Okay.
I just go with AK because it's easier for most.
Okay.
Sometimes Abdullah is hard to pronounce.
Sure. Yeah.
Yeah, so it's
Anyway.
just whatever easier, it's fine.
Okay. Cool. Yeah. So I was talking with AK a little yesterday, and so again, this exam will be the same like format as the first one, where you will, if you haven't already, like today or tomorrow, you should call the testing center and like tell them that you're coming on Thursday morning to take the exam, and then it'll be basically just the same as the last one in terms of how you set it up, how you go in there, and how you do it. Did it all end up being easy enough for you all to do that?
Yeah, will it be the same in Idaho Falls?
Yeah, it'll be the same as what you did before.
Okay.
Yeah, is there anything I can still like contact them and tell them different specific directions if there was something that didn't work last time?
Yeah, I had to reserve the time last time online.
Okay.
I remember which link, but I could probably do that again.
Okay. Yeah, let me know if you are having trouble finding that link again. So that all should be the same. And then I think too, they in Pocatello, they told me, like I told them, it should, you should have like this 90-minute window that starts at 8. And they said, well, we takes a minute to check in people and we open at 8. So I think maybe this is what happened last time, but you should be able to get like 90 minutes from when you're able to check in if you're like, in line at 8 a.m. So if you're like there at 8 and it takes you like 5 minutes to check in, they said they would give you like till I guess 9:35. So but I guess they'll tell you more, or you can ask them specifically. Any other questions about the format or anything?
You know how many problems are on the exam this time?
Yes, I double check. I believe I wrote 5 problems. Yeah, there'll be 5 problems. Yeah, so there'll be 5 problems on the exam. They will cover specifically the material related to magnetostatics and time varying electromagnetics. So this is basically the homework 5, 6, 7, and 8. I'm not asking any problems specifically related to things like Coulomb's law or electrostatics, or questions like mathematic questions like on solving a Stokes theorem problem. However, right, that doesn't mean that you can't just forget all of that stuff, because all of the vector calculus that we reviewed in the beginning of the class, right, we're still using that vector calculus. And then, I'm not asking like questions specifically about like say Coulomb's law, but almost every step in the Biot-Savart is identical to the Coulomb law steps. So make sure that you still understand those previous concepts, because those concepts are something that we'll be continuing to use in this exam. So yeah, five questions. Trying to see where I put it. I think when you take the exam, I think I told you this last time, but do be sure to take a look at the point total on the top of the page or whatever, because the higher the point total, the more difficult the question is. And there's at least 1 or 2 questions that are, I think, are a little more time consuming than 2 or 3, or at least 1 or 2 of the other questions. So do be sure to take a look at that. There will be, just like the other exam, the first few pages of the exam, those are going to be cookbook, or your cookbooks. Okay. So in the first few pages of the exam, there's going to be all of that vector calculus cookbook. So the first one that we started with, right? So this is like the chapter 3 stuff. And then there will also be the vector cookbook. So basically all of your vector calculus, and then all of like your coordinate systems, all that kind of stuff, those are going to be in the front. So that's like kind of the early stuff we covered. And then there will also be the cookbook on the Ampere's law, so that the steps describing how to apply like the symmetry case and solve Ampere's law. And then there will also be the Biot-Savart cookbook in there. So there's those 4 that are going to be in there in the front. Yeah. So those will be in there in the front. You can bring your, you can bring your page of notes front and back to the exam. Bring that page of notes front and back to the exam. You'll have a bunch of those cookbooks, and then you can use all of that to solve the 5 exam problems. Other questions?
As far as the exam goes, we're just gonna have like very basic like integrals and derivatives, right?
Yeah. Yep. So it should be something that you either, so there's either going, and yeah, I didn't put in any tables with a bunch of, tricky integrals. So the problems are either going to be, if there's derivatives and integrals, it's either going to be something that you should be able to, remember from your calculus class because it's, fairly straightforward, or it should be something that is, pretty easy to punch in onto your calculator that can do that. But it's not going to be something that's like, so tough that you need Wolfram or Mathematica or Maple or something to solve for. So the problem would stop if at the end of the setup if there's a problem like that. So good question. Other questions? All right, so I'm here to answer questions for you that you might have about the exam. So if you have questions or things you want to review, then let's talk about those. And if there's not a lot, let's, I can give you the time to study. So
can we discuss that displacement, current, and conduction?
Current and conduction?
The displacement, current, and conduction.
Yeah, that's good. Okay. So yeah, that's a good question. Let me pull out. Textbook is a supplement. So, okay. Now, the displacement current is basically you can almost think of it like an artifact or a additional term to some of our Maxwell's equations that describes another way that we can get current. Okay, so in the classic way to think about where displacement current exists is going to be in a capacitor. Okay, so when you have a capacitor, well, let me back up another second. How do you normally think about what current is? What do you normally think of as current? What's the classic answer for what is current?
All of electrons.
Yeah, moving electrons. And is it okay to even generalize that to saying moving charges? Would that also work?
Yeah.
Yeah, that also works. So the classic, if someone says, what is a current? The classic thing to answer is, well, current is moving charges. But there's some other cases, right, where we don't have moving charges, but we still expect to have a current, right? So and the most classic one is going to be on a, a situation where we have two large parallel plates together. And let's connect them to a voltage source that is sinusoidal. All right. Okay, so we got two large parallel plates like this. We connect them together to this battery. And right, we can solve for the current, right? You could solve for the current here, right? You could solve for a current that's here. And would that current be the same as the current here?
We'll just have different polarities, so science.
Is it a different polarity?
The same, but sorry, it's the same.
Yeah. So this is a conduction current, right? It's in the wire. But then we get to this case here, and this is where people realize, okay, there might be a problem. In this region, are there any moving charges?
Yes.
So in this region, right, there are not moving charges, right? There aren't actually charges that are jumping across these plates. They're building up on the plates. And eventually, right, in steady state, right, the buildup will be equal, but opposite to the voltage here. But the charges aren't crossing over, but the electric field is changing in this region between the two plates. And so that led people to realizing that this equation was not going to completely describe the current. Okay, so the relationship between the magnetic field and the current is not completely described by this equation. And so they needed another term. They needed another term to describe what was actually happening in this region between here. So there's some field here that is not completely described by the moving current because, right, there isn't actually moving charges in here. And so that term is this term. And what does this describe? What does this mean? What does it mean, and what are the units on this term that I just added?
The change in was it field density
Mm-hmm.
over
Yeah.
time?
Yep. So this is the change in electric field density with respect to time. And what would the units be on this? The units here are your amps or amps per something, right? So what are the units on this one? I didn't quite catch that.
Oh, is it amps per second?
Yep, yeah, so this one is also going to be amps, okay? So this means that this term has to have the same unit as current, but what it is not actually moving charges, it's moving electric field. And the change in the electric field is due to this, right? This is when you have a time varying source, this is going to cause sometimes, right? The top of this is going to stack up with positive charge and negative charge. And then sometimes, right, what's actually going to happen is the opposite way, right? Where we are building up negative charges on there and positive charges down here. And that's going to change as the time changes. And that change in time is going to create, right, this is an electric field, right? So if you have minus charges on top and positive charges down here, right, this is a potential. Electric scalar potential, or what do we normally call electric scalar potential? Yeah, normally we call that voltage. So if we have a time varying source, it's going to set up an electric field across these two parallel plates. As time changes, right, the amount of minus charges or positive charges on each plate that are congregating there, right, it's not going to just immediately ramp up, right? Like it takes a moment for this plate to charge up. And so that means that because it takes time for this parallel plate situation to achieve a steady state where it's balanced in voltage with respect to the battery or that source, right? Because it takes time for that to happen, that voltage is changing. And if the voltage is changing, that means that the field is changing. And if the electric field is changing, so is the electric field density. So that change in time, right? This means that we have a change in time, an electric field that's changing in time across these plates. And that change in time is a current. And that's what the current density is, okay? And this, it was basically like one of the last parts of the Maxwell's equations that had to be added in order to unify the magnetostatics with the time varying electromagnetics. Okay, so previously, right, when we looked at electrostatics and magnetostatics, right, we disregarded terms like this, right? The time derivative was equal to 0. But now, right, if we have a situation where the time derivative is no longer 0, we must account for it. And accounting for that gives us a term that is actually a current term. All right, so does that answer some of your questions, Daniel? Does that help you understand? What else can I tell you about the displacement current?
I get the concept.
Okay.
Is there any chance we could work some examples?
Yeah, we definitely can. And just so you know, though, there are very few simple problems regarding the displacement current. And also the displacement current is typically a very, very small number compared to the actual current. But let's go ahead and take a look at this. So, okay. So if we have a conduction current flowing through a wire with a conductivity of that's given, so does anyone know if this is a high conductivity of wire or a low conductivity or normal? Do you have a feel for what this number means? So this is a pretty high conductivity. This is about the conductivity, I think, of aluminum, which is like just a little bit less than copper. So 10 to the 7th is basically the conductivity of very conductive materials. So we have a current that's flowing through a wire, and you can imagine this as a wire that you might purchase for your own use in a breadboard kit or something like this. This is basically very conductive wire. Okay, so we have a current flowing through very conductive wire, has a relative permittivity of 1, and the conduction current is a sinusoid. With a radial frequency of 10 to the 9th. Excuse me. And we want to find the displacement current. So we have conduction current, and we want to find the displacement current. So for the conduction current, as long as it's flowing in one direction, we can simplify this from a vector down to a scalar, right? So in this situation, we can assume that this is essentially a scalar situation where we can sort of ignore the vector components and just assume that it's all going in the same direction. And we can also rewrite this like so, because, oops, pardon me. Right, this is kind of like Ohm's law in 3 dimensions, right, where we have the current, a conductivity, and something related to voltage. Okay. So if we were to write it this way, can you find an expression for E, first of all? So can you find an expression for the electric field that's going to be across this set of parallel plates? So based on what I've shown you, can you find an expression for the electric field across those plates?
Yes.
All right, so take a moment then on your paper and do this.
10 to the negative 7 sine WT.
Is 1 to the what?
1 times 10 to the negative 7 sine W.
Like this? Okay. All right. I think that is probably close. However, we don't actually know what the area is. So if we wrote out this, we could leave in the area where we have over area. Okay. Now, we also know that the displacement current density would be the displacement volume current multiplied by the area. So if you have some displacement current like this, we could write this term as the conduction current and the displacement current. And if we were to do that, right, we could write an expression for our current here as being equal to this. And we also know, right, that we have this expression. And because we're dealing with a little bit of a scalar simplification here, right, we're dealing with a full circuit. So because of that, it's a little inconvenient to use vectors because the current is moving, changes vector direction. So we're kind of doing a little bit of a cheat. We're converting from vector into scalars by assuming, right, that the whole circuit here is oriented in the same direction. Okay, does this derivation make sense? How I arrived here?
Yes.
Okay. So for this displacement current density, I substituted our expression for the changing electric field. And I used this this epsilon. And then what will epsilon be? Do you remember? We can write this usually as two terms. There's two different things that we usually write this as. What would we call it in terms of the variables? One is epsilon naught, right? What is the other variable?
ER.
Yeah, ER. And we know what that is, right, from this. So in our case, right, epsilon should be equal to this, right, because we have ER equal to 1. And then in the previous part of the problem, we found this.
Would that be 10 to the negative 10 or 7?
believe so.
The current was in milliamps.
Yeah, so this should be, let's check. So 2 divided by, yeah, and then this is in milliamps.
Okay.
And I think that I forgot that here. I apologize. I should have been writing units, right? Do you get this?
Yes, I didn't use the milliamp.
Okay. Yeah, that's my bad. I apologize for that. Okay. All right, so we have this for our field, and then this one is in volts per meter. Okay, so now can you find the displacement current? So take a minute and write this, right? We found an expression for what this field should be. So substitute in, take the derivative, multiply by this, check if anything cancels, use this, right? Epsilon naught information, and come up with an expression for the displacement current. And I'll also just
I got 1 times 10 to the negative 10 EW cosine W.
W. I think you can simplify it a little bit more, because right, this, we know what this is. We know what this is, and we know what the omega is. Anyone else get an answer? And in your calculator, right, this one should be 1, at least on mine, right? This is 1E9.
I got 8.85 times 10 to the negative 13 cosine 10 to the 9th t,
Yeah.
or omega, yeah, or just omega, yeah.
All right. Yes, this is also what I got. Okay, so this is the displacement current. And the conduction current was, it was in milliamps. Like this. Okay, so what do you notice about these two? The conduction current and the displacement current. I guess first off, which one's bigger?
Conduction current.
Yeah, by how much, Cade? Like a small amount, a medium amount, or an enormous amount?
Pretty big amount.
Yeah, the conduction current is like way bigger than the displacement current. Like 10 orders of magnitude. It's so much more than the displacement current. So this is a very, very small term. What else do you notice about the conduction current and the displacement current? What other difference is there?
They're 90 degrees out of phase from each other.
Yeah, they are not in phase with each other. So the displacement current is actually out of phase compared to the conduction current, and that's due to this time derivative here. What else can we say about this? What are some things that could make the conduction or the displacement current larger? How could the displacement current become a larger number?
The plates are closer together.
Yeah, let's see. Is there anything related to the plate distance? Don't think there's anything related to the plate distance. But there are a few things that we could think about. So let's see. If this number becomes smaller, so if the conductivity goes down, what happens to the electric field? What happens to this amplitude?
Goes down.
So let's see. Yeah, if we make the denominator a smaller number,
Gets bigger.
then this answer is going to be bigger. So if we have a less conductive wire, we'll have a larger electric field amplitude, which would result in a larger displacement current. Does that make sense? So if we make this number bigger, if we make the amplitude here, so if we make this number go bigger, then it'll make the displacement current go bigger. What about if we increase the relative permittivity of the wire?
Gets bigger too.
Yeah, that would make it bigger. If we made the if we changed the wire cross section, what would happen? What if we change this?
Gets bigger too.
Yeah. So if we have very small diameter wire, if we have very high conductivity wire, then the displacement current is very small. Okay. So usually we can just ignore this displacement current, even even when the time varying field exists. So this is why when you go into the lab and you build a circuit and you use a sinusoidal voltage source, this is why you're almost always going to just ignore the displacement current, is that you're going to be using small diameter wire, highly conductive wire, and you'll just be able to assume that this displacement current is a very, very small number and is not going to affect your problem very, very much. Yeah. So the displacement current, I think we really only covered the one problem on it. There's one homework problem. There's no quiz problems on it. The displacement current is important because you should know that it exists. You should know that it unifies the Maxwell's equations, but you should also know that in most practical situations, in basic electromagnetic problems, we don't need to deal with it. So that's I think kind of what we should take away from the displacement current. Any other questions? Do you believe that displacement current exists?
Yes.
Yeah, I do too. It's just a small number, but yeah, if you want to like get into you know, I'm not encouraging you to get into like, you know, electrical engineering conspiracy theories or anything, but this is probably like, if you look up, I mean, there's all kinds of like free energy scams or whatever if you start searching YouTube, and most of them involve some form of not believing in this unification of Maxwell's theories via the displacement current. So I guess that's just some broader context for how non-engineers and non-scientists think about our field. So, all right. Other questions? All right, well then I have a problem that might be interesting. Let's imagine, oops, see if I can draw this better. So we did this. We solved for the electric field of this ring, right? But what about the magnetic field of this ring? Let's find it for some point. On the z-axis. So what way would you solve this? First of all, how'd you find the magnetic field? So we got two choices. What are the two choices? Let's start there.
Ampere or Biot-Savart.
Yeah, yep. So we got Ampere and Biot-Savart. Let's see who. AK, which one do you think we should use for this? So the Ampere is for very symmetric problems, and VO_SAVART is for any given problem.
Should we go with the VSR?
Yeah, I think VO_SAVART is the way I would go for this one. So pull out the VO_SAVART cookbook. And see if you can get these first 5 steps done. I forgot one more thing that would be useful to know. You may have given this, but let's say the radius is A on this. So the loop, yeah. The loop has a radius of A. Let me know when you have an answer for step 5.
I got negative x in x direction, negative y in y direction, plus zp in z direction.
Okay.
The root of x squared.
All right, yes, I believe this should work. Is there, so we have a circular ring. Is there a reason that you chose Cartesian coordinates, Daniel, instead of like cylindrical or spherical?
I guess I just like Cartesian more.
Okay. So if you were to convert this to cylindrical, so I mean you can do either one, but you should get this. And I believe those are the same thing. Okay, so that means that the unit vector, right, would be look something like this. Now, what about the current that is moving on that loop? So the current, right, is moving around in a in the phi direction, and it has a magnitude I, and then the dl for phi is r d phi. So for step 7, when we get there, right, we need to take this. All right, so what is the r directional component?
I already see 5.
What is the phi directional component?
0.
What is the z directional component?
0.
Are you sure on that one?
Sorry, negative AIRDC.
Okay, perfect. So now we have this cross product. We're going to integrate from the start of the current to the end of the current. And we had okay, does anyone see anything wrong with what we're about to do here? Do you remember from the electric field problem? What's going to happen when we try to integrate this radial this R, when we try to integrate in the R hat direction, all the way around phi. Does anyone remember what happens when you try to do that?
Don't we just get a 2 pi?
Yeah, but is that what it should be? Do you remember? So this is actually, there's going to be a bunch of canceling fields, and there's two. If we try to solve this in the cylindrical coordinates, this is going to be non-zero, but it really should be 0. And if you solve in Cartesian coordinates, you will get 0. And the problem has to do with this like complex math thing related to curvilinear coordinate systems. But basically this should be 0. And you can see this in Cartesian. So the route that Daniel is going will show this to you. So really, it's okay if you wanted on this problem, like where we're in cylindrical coordinates, you could either convert it to Cartesian, or you could just recognize, oh, and I apologize, this should be all over the RSP cubed, which will be this a squared. So you could either skip this R hat integration, R hat directional integration in the cylindrical coordinates, or you could convert into Cartesian coordinates and solve this. If you want to get a little bit more information on this, you could go back and check the Moodle. Okay. Where we looked at these problems here. Okay, so where we found the E field for the annular ring. I just wanted to bring these up because these are very classic, like solving for electric field and magnetic field for rings, disks, cylinders. It's a very classic problem, but you in electromagnetics, but you run into some integration situations. And if you look at this, right, this result will not make sense. So this is the same situation where we tried to integrate in the R hat with the d phi. This will not work in cylindrical coordinates. You have to convert to Cartesian, which takes a moment. But when you do that, what you end up with is that you get this 0 answer in the X and Y direction, which is the same as a 0 answer in the R direction. And so for the electric field, you only end up with this Z result. Same thing is actually going to happen for the magnetic field. So you can check this later if you like, and also look in the book. But I just wanted to make sure that you all remembered that and saw this, since it's kind of a classic problem in magnetostatics also. So if you have any questions, feel free to stick around. You can email me over the next couple days if you come up with any questions. Good luck on studying, and I'll see you all next week.
Thank you.
Yep, see ya. Gabriel, you got any questions?
Questions?
No questions?
Yeah.
Okay, I'm again having a lot of trouble understanding you, so maybe if you sent me a chat, send a chat. I'm not. Okay, all right, well, class is done, so you're welcome to log off if you'd like.